Hello, my name is Doug Johnson, and I'll be presenting my group's design project for ME325 Machine Design course at Iowa State University. One thing that has been done here in Iowa is looking at ways of replacing fossil fuels, coal specifically, with renewable energy sources such as wind energy for electricity generation. The decision was made to look at a model for household use that would supply enough electricity for an individual's needs. A form of powertrain is needed because the high rotation velocities required for electricity generation. If a wind turbine were to spin at the speeds necessary to directly spin the shaft, current designs would fail. This powertrain allows us to step up the speed to generate electricity while maintaining a safe turbine blade speed. The engineering assumptions made in order to design the gearbox are required power output of 2 kilowatts for electrical generation. This requires 3 horsepower through the gearbox. The lifetime of our wind turbine has been set for 10 years, running at full capacity for 16 hours each day. The blades of the turbine were assumed to be rotating at 40 RPM for full capacity power generation. Using the RPM of the turbine blades and putting through the gearbox to reach 1000 RPM for power generation, a 25-to-1 gear reduction is required. Through all of this, the minimum safety factor applied to all components is 1.2. Bearings contained within the housing are press-fit into the housing, while all other bearings are held in place by snap rings. Keys have been exaggerated in order to be visible, where in reality the analysis shows that the keys required are very small. As rotation is occurring, it may be hard to see this. This is because the large increases in speed make it hard to render and see the rotations as they are happening. Components of the gearbox were chosen for simplicity for such a small wind turbine, as well as reduction in cost. Spur gears were chosen because of these cost issues and their simplicity. When maintenance is required, spur gears are readily available, easy to replace, and cheap. The choice of spur gears also plays a big part in the selection of bearings. Helical gears require angular contact bearings in order to withstand the thrust loads traveling through the shaft that they create. We were able to use Timken 308W ball bearings for applications and loads. The shaft diameter is chosen largely by the bore requirements for our bearings. The necessary maximum shaft diameter in order to fit these requirements is 1 9/16 inches. Bolts were chosen as fasteners because of their ease of assembly and disassembly, as well as cost. There are a total of 14 bolts placed around the housing in order to keep the gearbox protected from the environment. Materials selection play a big role in design, as well as safety of each material component. In order for the gears to be able to withstand the large stresses that will be applied to them, avoid pitting and bending of the teeth, AISI 4142 is used. This steel has a very high Brinell hardness factor of 560 and a large ultimate tensile strength of 325 kilopounds per square inch. The steel chosen for the shafts also plays a big part in determining the factors of safety. Using our chosen steel, it was determined that we were able to come up with factors of safety of larger than 4.3. Doug Johnson was responsible for the narration of this video, as well as the analysis of the 2 sets of gears used. Ben Rome was in charge of shaft and key analysis. He also took care of final editing and compiling of all our analyses. Ben also did the shaft and gear modeling for analysis. Micayla Haugen worked on bolt analysis as well as the housing modeling for the gearbox. Brandon and I took care of bearing selection, as well as modeling the shafts, gears, keys, bolts, and model assembly. He also performed the finite element analysis for a shaft, Brennan was also responsible for the video and its editing.